Hello, welcome back to the Looc. In this segment, first we look at sealed methods and classes. A method declared sealed in a base class cannot be overridden in the derived class. So sealed basically bans overriding. Methods that are declared private are implicitly sealed. Methods that are declared static are also implicitly sealed because static methods cannot be overridden either. A derived class method declared both override and sealed can override a base class method but cannot be overridden in further derived classes. And of course, the sealed methods are resolved at compile time. This is known as static binding, as opposed to polymorphic binding that we saw in the previous segment, which is dynamic binding. Dynamic binding that is resolved at runtime or execution time is also known as late binding. Static binding that is resolved at compile time, that is when we write the code, is also known as early binding. If there's a sealed method, the compiler can decide to inline it for small and simple sealed methods. It improves performance. Inlining means that the method call actually replaced by the implementation code of the method call. So it is physically inserted. At that point, this improves performance because it avoids the overhead associated with method calls. A class that is declared sealed cannot be a base class. In other words, we cannot derive classes from it. And the sealed class methods are implicitly sealed. An example is the string class that we use a lot in our programs, a sealed class. It cannot be derived, and applications that use strings rely on the functionality and only on the functionality of strings objects as specified in the framework class library. A lot of classes are sealed in the framework class library for the same reason. Trying to derive from a sealed class is obviously a compilation error. The next concept we look at is called an interface. Interfaces are used to define and standardize the ways in which people, systems, in case of programming, parts of a program interact with each other. A C# interface describes a set of methods that can be called on an object, but without any implementation. So they really provide only method signatures that are supposed to be implemented in classes that implement the interface. It's called implementation as opposed to extension or deriving. An interface declaration begins with the keyword interface and can contain only abstract methods, properties, indexers, and events. Members are implicitly public and abstract, and an interface can extend one or more other interfaces to add detail to it. So as a result of the implicit public and abstract nature, it's a compilation error to explicitly declare so. And of course, an implementation detail would be a compile error because the essence of interface is that they are fully abstract. A class that uses an interface and implements it uses the colon operator in the class declaration, so the syntax is the same as for derived classes. And a concrete class implementing an interface must declare each member on the interface that was specified in the interface declaration. Uh, and if a class does not implement one, it must declare uh, it abstract and has to remain abstract in the class. Um, so if you don't define or declare as abstract or define by an implementation of every member in an interface, that's a compilation error. So interfaces have lots of similarities with abstract base classes, both in their intent and in their use, as well as in their syntax. However, there is a difference that abstract base classes can contain concrete methods that have implementations in them, in addition to abstract methods. An interface can have only abstract methods, so it cannot contain implementation. So that's the main difference. The other is that in C#, there can be only one base class for a derived class. It's called single inheritance. So C# as a language similar to Java doesn't allow something called multiple inheritance, when a class can inherit from more than one base class, and that is a construct that is allowed in the language C++, but not in C# and Java, and for good reason, because multiple inheritance can cause many subtle and hard to debug problems and ambiguities. Unlike with interfaces, a class can implement any number of interfaces, so there's no limit to that. A class can implement any number of interfaces, but can inherit only from one base class. Generally, an interface is used to capture the commonality of unrelated classes that are not necessarily in an inheritance hierarchy, and the interface describes the desired functionality, and the classes that implement their interface implement it. They can implement it different ways. Different classes can implement it different ways, only the signature is the same. And an interface is often used in place of an abstract base class when there's no default implementation to inherit. There are no fields and no default method implementations. The moment we have some implementation detail in an abstract base class, it will be a class, not an interface. Like abstract classes, interfaces are typically public types, contain public types, and they are normally declared in files by themselves with the same name as the interface and the .cs file name extension. It is also common to start their name with a capital I as a reference to interface. In our example, we develop an IPayable hierarchy where RPayable is an interface. So the purpose of the application is to determine payments for employees and invoices alike, and therefore we create an interface named IPayable. Employees and invoices are very different type of objects, so there's no inheritance is a relationship between them, and they are also not really subtypes of a more abstract type. So IPayable is not really a class in the sense of having derived classes, but employees and invoices have some aspect in common, and that's that payments can be made to them, and this is the situation calling for an interface. In our case, the IPayable methods include getPaymentAmount that returns a decimal amount to be paid for an object of any class that implements the interface, so the amount that can be paid to either for an employee or for an invoice. And typically we start with a capital I, their names, to distinguish them from classes. We want to implement give methods so-called talking names that describe the purpose of the method. The UML class diagram shows the class hierarchy. So at the top stands an interface I payable. The box indicates it's an interface in those two little quote-like symbols called guillemets. And invoice and employee are two classes that implement the interface. Note the dotted arrow, or dashed arrow pointing up, as opposed to solid arrow. Solid arrow indicates inheritance. Dashed indicates an implementation of an interface. And under employee, there is the salaried employee, which is actually a derived class. So there's a solid arrow pointing up. So employee is a base class. Salaried employee is a derived class. Employee is also an abstract base class. Its name is kind of italicized, and iPayable as an interface that captures the common aspects of invoices and employees in fully abstract ways. UML places the word interface in guillemets, and the dashed arrow is a relationship called realization, or implementation. And that stands in contrast of inheritance, where we derive a class from a base class. So here is the iPayable interface. It's very short because general interfaces are fully abstract, so there are no implementation detail, only method signatures, and in this case there's only one, get payment amount. And the signature is that it takes no parameters, an empty parameter list, and it returns a decimal amount. And that's all the iPayable interface declares, that everything that is payable has to have a get payment amount method that returns a decimal and takes no parameters. This will be valid both for employee and invoice. So one of the classes that implement the interface or realize the interface is invoice. iPayable, it shows that this class implements the iPayable interface. The syntax is the same as for inheritance. So this invoice could extend technically a base class called iPayable, but that's not the case, and the way we know that is because the capital I standing in front of iPayable, so we know that it's an interface, and invoice implements it as opposed to extending a base class. Invoice has two private, one integer and one decimal attributes, quantity and price per item. Has a property part number, which is a string, and another called part description, which is also a string, and then a 4-parameter constructor in which we pass in this 4-parameter the part number, the description, the quantity as count, and the price per item as price, and we set those in the body of the constructor. We implement properties to provide setters and getters of the quantity and price per item attributes. So here they are. There is validity checking, that's why we implement them. So quantity has to be non-negative, and price per item also. We override the toString method of the object class, so we output formatted string that consists of those components: part number, description, price per item, quantity. And of course we must implement the get payment amount that the interface declared. Of course, no implementation there because it's always abstract in an interface, so the implementation is here. Return quantity times price per items, that total price for an invoice for a particular part ordered in a particular number of quantity. So it's important again to remember that there is single inheritance in C#, so we can inherit from only one base class, but any number of interfaces can be implemented. A comma-separated list of interfaces would follow the colon if there are multiple interfaces, and we inherit from the base class but implement the interplaces, and the class declaration therefore must list the base class first if there are both a base class and interfaces, and then a comma-separated interface name. So comes the employee class, implements also iPayable, has a three read-only properties: first name, last name, and social security number, private setter to make it read-only, and a three-parameter constructor. It has a toString method. The properties are auto-implemented, and a toString method overrides the object class implementation, a formatted string that prints out first name, last name, and security number. Now we have to provide an implementation of get payment amount because of the interface, but this base class is too general to actually provide an implementation, so we defer the implementation further to derived classes, making this an abstract base class, and therefore we add the method get payment amount to in the right return type and the parameter list to this class, but with the abstract keyword indicating that, well, actually we don't provide an implementation, but we know we should, but we are deferring it, delaying it to be done in derived classes. This makes this class, of course, an abstract base class, so no employee per se can be instantiated. And then here is the one and only concrete class that we use in this example, the salaried employee. Derives, extends from the employee class, has a weekly salary private decimal attribute, has a 4-parameter constructor, which the first three are same as the employee base class, first name, last name, social security number, and in addition we set the salary, which is implemented as a property with the setter and getter method with validation in the setter. And here is the actual implementation of the get payment, which is implements the one in the iPayable interface, and that was abstract in the base class. So here we provide an actual implementation, return weekly salary, and we also override the toString method, displaying the base class toString method and followed by the weekly salary. So that will be our program. And if there are further derived classes, they all have to implement get payment amount, and this is basically now that takes the place of what we called earnings in previous in the previous version of the program. And the class implements an interface. It's an is a relationship similar to the inheritance. So they are similar in their implementation of an is a relationship. So we can think of them in similar terms, but there is the difference that an implement cannot have an interface cannot have any implementation in it, so no code. and when passing them, the same rules apply, and they are polymorphically passed. Our test harness payable interface test illustrates the iPayable interface and how it is used for invoices and employees polymorphically in a single application. So here is the main class payable interface test, and in the main method we create a 4-element array of payable objects. So we can invoke a constructor on an interface like if it were a class, and well, actually it's not a constructor, it just declares iPayable. That was wrong. So it just a 4-element array of iPayable objects, and now we populate the array, and we call the constructors of the actual concrete classes. So only concrete classes can have constructors. Abstract classes and interfaces cannot. So there's 2 invoices and 2 salary employees. The 2 invoices are one is for 2 seats and $375 each, and the second is for 4 tires, $79.90 each, and the 2 salaried employees are John Smith with his weekly salary and Lisa Barnes with her weekly salary. And then invoices and employees processed polymorphically. So we know already what to expect, that we will loop through the array. Here it is for each were current payable in payable objects. So since current payable is we don't have a base class for it, which is indicated that it's a variable name simply, can be all kind of types, in this case 2 invoice and salaried employees, salaried employee, and in payable object, where payable objects is the array that we just created. And so we loop through the array, and we write the get payment amount as payment due for each object by using the get payment amount. And the output will look like this polymorphically. Invoices, 2 invoices, 1 for 2 seats, and the payment due is 2 times the item price, and 4 tires, the payment due is 4 times the item price, and then the 2 employees with their weekly payments. So if you look at this program running, then at the root of it stands the iPayable interface. So its name is iPayable, and it declares only a shared method that every class that implements this interface must have: get payment amount, empty parameter list, decimal, return type. Then we have the invoice class, which implements the iPayable interface, has a quantity and a price item, integer and decimal, as well as auto-implemented properties, part number and part description, and a 4-parameter constructor that sets those 4 components. The quantity and price item setters and getters, with the setter providing validity checking, and the toString override that returns the formatted string that displays the part number, part description, the quantity and the price per item. And finally, the must, namely the get payment amount implementation that the interface mandates. So again, the invoice class with its attributes and properties its 4-parameter constructor, the property implementations, and the toString override and the required get payment amount, which in this case returns quantity times price item. Next is the base class employee, which also implements the iPayable interface, has a toString properties, first name, last name, auto implement 3, first name, last name, and social security number all auto implemented, read onlys, a 3-parameter constructor as a result, first name, last name, social security number passed in, and a toString override method that displays all these the first and last name, and then a new line, the social security number. And this class also must have a get payment amount. If it does not implement it, then there is only one choice, and that is to declare it abstract, an abstract method, and delay implementation to derived classes, and that of course means that this employee class is an abstract base class. The concrete class derived from it is salaried employee. So salaried employee extends employee, has a weekly salary private decimal attribute, a 4-parameter constructor of which 3 are inherited from the base class, and the 4th one is added as salary, a property implementation that defines the setter and getter, with the setter or mutator performing validation, and the get payment amount finally gets implemented in this derived class by returning weekly salary, and there is a toString override as typical with overriding the base class version but invoking it and adding additional information to it. So that's the salaried employee class. The test harness payable interface test has the main method in which we declare an array of 4 iPayable objects. So iPayable and interface is like a type, an ADT, an abstract data type, but not defined by a class, but defined by interface. And for each element we invoke various constructors, 2 invoice and 2 salaried employee constructors. The only thing that connects them, that both of them implement at some point the iPayable interface. Salaried employee actually extends employee which implements, so it indirectly implements the iPayable interface. Header invoices and employees processed polymorphically, and then in a generic way we loop through the payable objects array where a variable current payable in payable object. Again, since current payable can be a variety of different types that don't even share a base class, so we just declare it as a variable where current payable in payable object, and then console write line, and we display their get payment amount. We display the current payable and the get payment amount, and the current payable invokes the toString method of each. So if we save and build this program, then we can check the output, which is takes a few seconds. And Control F5 to run the program, and here is the output. So we see the 2 invoices and the 2 employees displayed. Processed polymorphically, in our loop, for each loop. So there are the the two seats, the four tires, and John Smith and Lisa Barnes with their two-string methods invoked, and the get payment amount displayed as payment due, and that's the method that they both implement from the iPayable interface. So that was our interface implementation example. I did some summaries here so that we avoid confusions that can arise from concepts that are similar but not identical. So virtual versus abstract function. A virtual function is a function that can be overridden. So it provides a function, an implementation that may or may not be good for a child class. If it's good, then there's nothing to do. The derived class or child class inherits it. If not, then we can override it and provide functionality appropriate for the derived class. So the virtual keyword indicates permission to override. So this method can be overridden. Unlike sealed, which cannot be overridden. An abstract function, on the other hand, has no implementation of code. Any child class must implement this method because the base class is too general to define even a partial implementation. They are implicitly virtual, and the abstract keyword in the C++ language is not there. They are called pure virtual functions in C++. So there's a distinction between virtual and abstract functions. Abstract base class versus interface are similar but different concepts too. An abstract class is a class that cannot be instantiated but can contain code, but doesn't contain all the code to create an instance, so some methods are abstract in it. An interface, on the other hand, contains only method definitions but no code at all. So when an interface is implemented, all methods have to be implemented that are defined in the interface. If there is logic that is the same for derived classes, then it's better to use an abstract base class and put the logic in there that all the derived class inherit, as opposed to an interface. On the other hand, we have disparate classes that share absolutely no implementation detail, only the conceptual similarities of having similar methods. Then we use interfaces. It's important to remember that we can implement multiple interfaces but can inherit only from one base class. For usage generally between abstract base class and interface, the main difference is that a base class, abstract or not, can contain implemented members, and interface cannot have any implementation. If the concrete classes share some implementation, we use a base class. If they don't share, then generally an interface is used. And we also talked about a compile time or early versus runtime or late binding or static binding and dynamic binding. In case of a virtual method, the runtime type of an instance determines the method invocation. In case of a non-virtual method invocation, the compile time of an instance determines what version of the method is invoked. And this also means that a non-virtual method has an invariant implementation. In other words, the implementation is the same whether the method is invoked on an instance of a class in which it is declared or on an instance that is derived from it. In contrast, a virtual method can be overridden, superseded by derived classes, and the process of superseding an implementation is called overriding. And the virtual keyword provides dynamic or late binding and gives permission for overriding as opposed to non-virtual. And all methods of class object can be called by using a reference to of an interface type. All object inherits the method of the root class object. Some common interfaces in the .NET Framework class library are I-comparable, so they implement less than, greater than, less than equal, greater than equal to, equals, non-equals operators. I-component, I-disposable, and I-enumerator, which is generally an iterator type of class. Our final topic is operator overloading, which is a construct in C# that allows the programmer to overload actual operators, not just methods, method names. So operators like plus, minus, plus sign, minus sign, multiplication, division, and so on. So actual operators can be overloaded as well, like methods. As an example, we will use the example of complex numbers, which implements the overload of the addition and subtraction and multiplication. Could overload the division too, but there's a little more math to it than the first three. Using common mathematical notation. So here is the complex number class. It has two double read-only properties, the real part and the imaginary part, auto-implemented, and a two-parameter constructor that takes A and B as real and imaginary part. A toString that prints out three components, the real part, and then the imaginary part, which is actually consists of a sign and the absolute value, and if the imaginary sign less than or 0, then it's a minus sign, otherwise a plus sign, and the imaginary part. So, three components, a complex real part, a plus or a minus sign, and the imaginary part as well. So, so here are the constructors, and the imaginary part also has a little I following it. So the imaginary part is imaginary part times I, where I is negative, it is square root of -1. So here is the addition, overloaded, complex number static, that's what it returns. This overloads the plus sign. We cannot just put a plus sign, so the syntax is operator plus. This is coming from the C++ language that has operator overloading, unlike Java, which does not. And the syntax in C++ is like this. So public static complex number operator plus. Static shows that it's a class level construct, and it takes two complex number objects and returns a complex number object whose real part is the sum of the real parts of the two complex numbers plussed in, and its imaginary part is likewise. The same goes for the operator minus overload. Two, in the first case, two addends, in case subtrahends are added, and the difference of the real parts is the real part, and the difference of the imaginary parts is the imaginary part. And finally, the multiplication of two complex numbers returns a complex number made up of the product of the real times minus the product of the imaginary types as the real part, and the cross products of real and imaginary added together as the imaginary part that is common for complex numbers. So when we overload operators, we use the keyword operator followed by the operator symbol is used. Methods that overload binary operators, which are very common, like plus, times, minus, and divide. The first argument is the left operand, the second is the right operand. Overloaded operator methods must be public and static. And generally, non-intuitive use of operators should be avoided. So plus should really means adding things together and so on. At least one parameter should be a reference to the object in which class the operator is overloaded. This prevents changing operators on native types. So complex tests demonstrate how to add, edit, and multiply complex numbers. In the main method, we declare two complex numbers x and y, and add the real part of the first complex number, and we convert it with a read line, convert it to a double, and that will be the real part and the imaginary part likewise. And therefore, it is at two doubles, and x will be a new complex number and pass in the real part and imaginary parts, and likewise for the second complex number y, enter the real and imaginary parts and create the complex number, calling the constructor, and then we display calculation results. So a new line, and the results are first and second arguments are x and y themselves, and then connected by the appropriate operator plus, minus, and times, and then the result of these operations. And also shown is the output, so say 2 plus 4i plus 4 minus 2i, added together is 6 plus 2i. Likewise, the difference and the product of the two numbers is displayed. So note that in when we wrote the toString, we included the complex numbers with round parentheses, and the I, the imaginary unit, is always there, and as a result, in the output, we see the parentheses around the complex numbers. It may not be necessary, but it can help. So if we look at this program, then we have the complex number class with two read-only properties, the real part and the imaginary parts, both doubles, the two-parameter constructor, and then the toString methods, which displays a complex number in round parentheses, and the real part first, then plus or minus depending whether the imaginary part is positive or negative, and its absolute value. 0 is also accepted and will be displayed as 0i. And then the operator overloads, the plus overload, adding the real parts and the imaginary parts, the subtraction overload, taking the difference of the real parts and the imaginary parts, and the multiplication overload, taking the products of the real and imaginary parts and forming the product real and imaginary parts. So that's our complex number class. It's really a very classic class. At some point, typically any programming language we sooner or later implement complex numbers, especially if the language provides operator overloading. And the complex test, two complex numbers, and we enter them one by one using read lines and converts, and then invoke the constructor to construct x and likewise y, and then we display the results of those operations. So if we build this program, then it takes a few seconds to complete, and Control F5 will run it. So here is the result of here is where the input comes. So let's say the first number has real part 2 and has imaginary part 4, and the second has maybe real part 4 and imaginary part, say, -2, and those are the two complex numbers, and we see the result of the operations on them as performed by the overloaded operator plus, minus, and times. So it's important to see that in the code, in the x plus y, x minus y, and x times y are operators perfectly applicable to complex numbers because we provided the overloading for them, and it correctly computes the sum, difference and product of complex numbers. It might be a useful exercise if you are following this Looc to implement the division of two complex numbers, paying attention to the fact that even in complex numbers we cannot divide by 0. A complex number is 0 only if both its real and imaginary parts are 0. So that is the end of this segment.